Merhaba arkadaşlar, günaydın. Umarım iyisinizdir. Şu ana kadar bu derste işletim sistemlerinin genel tanımından bahsettik, genel yapılardan bahsettik. Ardından proseslerden, threadlerden bahsettik. E, Bu prosesleri ve threadleri nasıl sıralayabileceğimizden, hangi sırayla çalıştırabileceğimizden ve burada kullanabileceğimiz yöntemlerden, algoritmalardan bahsettik. Bu arada artık şeyi de biliyoruz. Hem elimizdeki işlemcilerin yapısı gereği birden fazla işlemci kullanıyor olmamızdan dolayı hem de işte paralelizm ve concurrency meselelerinden dolayı proseslerin bir de şey meselesi var tabii. Birbiriyle iletişim halinde olan prosesler var. Bunlardan da yine bahsetmiştik. Message passing ya da shared memory ile prosesler birbiriyle iletişimde kurabiliyorlar. Bütün bunlar aslında bize aynı veri üzerinde çalışabilen farklı proseslerin varlığını ifade ediyor. Dolayısıyla burada bir senkronizasyon problemi ortaya çıkabiliyor. Eğer aynı veri üzerinde ya da ortak bir veri kümesi grubu üzerinde işlem yapan birden fazla proses mevcutsa bu veride kimi tutarsızlıklara neden olabiliyor. Yani bir prosesin yaptığı değişiklikten diğer proses haberdar değilse ya da yapılan değişiklik orada bir problem yaratacaksa veride bir tutarsızlık olabilir ve bu da e, aynı veri üzerinde işlem yapan proseslerin yanlış şekilde, istenmeyen şekilde çalışmasına neden olabilir. Ee, Önümüzdeki derste çok bilinen temel senkronizasyon problemlerinden bahsedeceğiz. Bunlar soyut olarak var olan, soyut olarak çözülebilen, belirli bir soyutlama düzeyiyle çözülebilen ama hani gerçekte kimi durumlarda karşımıza çıkabilecek genel problemler. Ancak bu problemleri çözebilmek için öncelikle elimizde bazı araçlar olması gerekiyor. O problemleri çözüm üretebilmek için kullanabileceğimiz araçlardan bu hafta bahsedeceğiz. Senkronizasyon araçlarından bahsedeceğiz. Senkronizasyon araçlarının ardından dediğim gibi bir sonraki derste de bu araçları kullanarak bu senkronizasyon problemlerini nasıl çözüm üretebiliriz bunlardan bahsedeceğiz. Eğer herhangi bir sorunuz yoksa dersle ilgili ben doğrudan başlıyorum. Var mı sorusu olan? Slide'ı görebiliyor musunuz? Seste ya da görüntüde bir problem var mı? Yok sanırım. Başlıyorum o zaman. Okay, this week we are going to discuss the synchronization tools which we can use to solve synchronization problems. A cooperating process can affect or be affected by other processes while executing in the system. Cooperating processes can directly share a logical address space or be allowed to share data only through shared memory or message passing. However, concurrent access to shared data may result in data inconsistency. In this chapter, we are going to discuss various mechanisms to ensure the orderly execution of cooperating processes that share a logical address space so that data consistency is maintained. Okay, we have already seen that processes can execute concurrently or in parallel. In the previous sections, we introduced the role of process scheduling and described how the CPU scheduler switches rapidly between processes to provide concurrent execution. This means that one process may only partially complete execution before another process is scheduled. In fact, a process may be interrupted at any point in its instruction stream, and the processing core may be assigned to execute instructions of another process. Additionally, again, in previous sections, we introduced parallel execution, in which two instruction streams representing different processes, of course, execute simultaneously on separate processing cores. Also, we illustrated the problem when we consider the bounded buffer problem with use of a counter that's updated concurrently by the producer and consumer, which lead to a race condition. In this chapter, we are going to explain how concurrent and parallel execution can contribute to issues involving the integrity of data shared by several different processes. Okay, actually, an example is illustrated in this figure. In this station, two processes, P0 and P1, are creating child processes using the fork system call. You can remember the fork system call from previous sections. That fork returns the process identifier of the newly created process to the parent process. Okay, so you can use fork system call to create a new process, and that system call provides you an ID, an identifier of the newly created process. In this example, there is a race condition on the variable, on the kernel variable next available PID, which represents the value of the next available process identifier. Unless mutual exclusion is provided, it's possible the same process identifier number could be assigned to two separate processes. So this can be considered an example of race condition. We are going to begin our consideration of process synchronization by discussing a problem. Actually, it's called as critical section problem. Okay, consider a system consisting of n processes from P0, P1 to Pn-1. Each process has a segment of code called a critical section, in which the process may be accessing and updating data that's shared with at least one other processes. So we can create some sections. We can call them as critical sections. On critical sections, we are going to consider that that process is going to make some change on the shared data. So for that reason, that block can be named as critical section. The important feature of the system is that when one process is executing in its critical section, no other processes is allowed to execute in its critical section. That is, no two processes are executing in their critical sections at the same time, because they are going to try to update same data. For that reason, we are going to create a mechanism that no two processes are executing in their critical sections at the same time. The critical section problem is to design a protocol that the process can use to synchronize their activities so as to cooperatively share data. Each process must request permission to enter its critical section. The section of code implementing this request is the enter section. The critical section may be followed by an exit section. The remaining code is called as reminder section. So we are going to divide our process in different sections. There could be some enter section, there could be some exit section or reminder section. But if that process is going to make some change on the shared data, we are going to call that part as critical section. And we have to create some mechanisms that no two processes enter their critical section at the same time. Only one process can execute its critical section at the same time, at a specific time, actually. So here the general structure of a typical process can be shown. The enter section and the exit section are enclosed in boxes to highlight these important segments of code. Sorry. Sorry for that interrupt. So in this figure, you can see a typical process which has a critical section. So critical section means we already know that in that section, that process PI is going to make some change on the shared data. So before that section, we have an enter section and exit section. Based on the design of that enter section and exit section, we can create some mechanisms, we can create some solutions to critical section problem. So let's start to discuss the requirements for a solution. A solution to the critical section problem must satisfy the following three requirements, which are mutual exclusion, progress, and bounded waiting. Mutual exclusion means if process PI is executing in its critical section, then no other processes can be executing in their critical sections. So it's called as mutual exclusion. The second one is progress. If no process is executing in its critical section and some process wish to enter their critical sections, then only those processes that are not executing in their remainder sections can participate in deciding which will enter its critical section next. And this selection cannot be postponed indefinitely. We have to create a progress. All processes create their progress to complete their job. And the last one is bounded waiting. There exists a bound or limit on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. So if process A is create a request to enter its critical section. In a bounded waiting time, we have to provide that that execution of critical section. So we can assume that each process is executing at a non-zero speed. And however, we can make no assumption concerning the relative speed of the end processes. But if we want to solve the critical section problem, our solution has to create some mechanism, have to provide some mechanisms based on the mutual exclusion, progress, and bounded waiting. The critical section problem could be solved simply in a single core environment if we could prevent interrupts from occurring while a shared variable is being modified. In this way, we could be sure that the current sequence of instructions would be allowed to execute in order without preemption. No other instructions would be run, so no unexpected modifications could be made to the shared variable. Unfortunately, this solution is not as feasible in a multiprocessor environment. Disabling interrupts on a multiprocessor can be time-consuming since the message is passed to all the processors. So if you want to prevent interrupts, you have to pass that message to all the processors. This message passing delays entry into each critical section, and system efficiency will going to decrease in that station. Also, consider the effect on a system's clock if the clock is kept updated by the interrupt. So the uh, most simple solution based on single core environment can be described as interrupt based solution. We can prevent interrupts while a process in critical section, but it's not going to work in a feasible way on multi-core systems. Now, we are going to illustrate a classic software-based solution to the critical section problem, which is known as Peterson's solution. Because of the way our modern computer architectures perform basic machine language instructions, such as load and store, there are no guarantees that Peterson's solution will work correctly on such architectures. But still, Peterson's solution is a classical software-based solution. So it's going to provide some basic understanding about the solution of the critical section problem using software-based solutions. So we are going to represent this solution because, again, it's going to provide a good algorithmic description of solving the critical section problem. And it's going to illustrate some of the complexities involved in designing software that solve the requirements of mutual exclusion, progress, and bounded waiting. Peterson's solution is restricted to two processes that alternate execution between their critical sections and reminder sections. So this part is very important. Peterson's solution actually provides mechanisms for just two processes. The processes, let's assume that numbered as P0 and P1. For convenience, when presenting, we are going to use Pi and Pj to denote the processes. So that is J will be equals 1 minus I. So we have Pi and we have Pj. Peterson's solutions requires the two processes to share two data items. We have an integer turn and a Boolean array flag. So let's say we have two processes, Pi and Pj, and they're sharing the same variables, which are turn and flag. Pi and Pj sharing turn and flag. The variable turn indicates whose turn is to enter its critical section. So it will be Pi's turn or Pj's turn. So turn variable is going to indicate that whose turn is to enter its critical section. That means if turn equals I, then process I is allowed to execute in its critical section. The next variable, the flag array, is used to indicate if a process is ready to enter its critical section. For example, if flag I is true, that means Pi is ready to enter its critical section. So turn equals I means Pi is allowed to execute its critical section. Turn equals J means Pj is allowed to execute its critical section. And if flag I is true, that means Pi is ready to enter its critical section. If Pj is true, that means Pj is ready to enter its critical section. And turn and flag are shared by Pi and Pj. So here is the algorithm for process I. With an explanation of these data structures complete, we are now ready to describe this algorithm. To enter the critical section, process Pi first sets flag I to be true, because flag I true means process I is ready to enter its critical section. Then sets turn to value j, not j. So thereby asserting that if the other process wishes to enter the critical section, it can do so. Process I set the turn to j. That means if the flag j is true, process j can execute its critical section. So we can creating a mechanisms to allow the other process to enter its critical section. If both processes try to enter at the same time, turn will be set to both I and j at roughly the same time. Only one of these assignments will last. The other will occur but will be overwritten immediately. The eventual value of turn determines which of the two processes is allowed to enter its critical section. So after the critical section, let's assume that PI execute its critical section. After the execution of critical section, it's going to set its flag to false. That means, okay, I execute my critical section and now I don't need to execute critical section again. I'm not ready to execute my critical section. So based on that, if process J needs to execute this critical section, it can enter that section. So we have to check the correctness of our solution. We now prove that this solution is correct. So if you want to prove that, we need to show that the mutual exclusion is preserved, the progress requirement is satisfied, and bounded weighting requirement is met. To prove property 1, which is mutual exclusion, we note that each PI enters its critical section only if either flag J is false or turn equals I. So at that time, flag J equals true and turn equals J, and this condition will persist as long as PJ is in its critical section. As a result, mutual exclusion is preserved. Just PI or PJ can enter its critical section. Both of them cannot enter their critical section at the same time. So basically, we are creating that mechanism for mutual exclusion. To prove other properties, properties 2 and 3, we note that a process PI can be prevented from entering the critical section only if it's stuck in the while loop with the condition flag J equals true and turn equals J. This loop is the only one possible. If PJ is not ready to enter the critical section, then flag J will be false and PI can enter its critical section. If PJ has set flag J to true and is also executing its while statement, then turn will be equal I or turn will be equal J. So if turn equals I, then PI will enter the critical section. If turn equals J, PJ will enter the critical section. However, once PJ exits its critical section, it will reset flag J to false, allowing PI to enter its critical section. So if PJ resets flag J to true, it must also set turn to I. Thus, since PI does not change the value of the variable turn while executing the while statement, PI will enter the critical section. So it creates a mechanism for progress. After at most one entry by PJ, and that satisfies the bounded weighting requirement. As we mentioned at the beginning of this section, Peterson's solution is not guaranteed to work on modern computer architectures for the primary reason that to improve system performance, processors and or compilers may reorder read and write operations that have no dependencies. So we cannot guarantee that read and write operations which have no dependencies is going to execute on the same order. So for a single threaded application, this reordering is immaterial as far as program correctness is concerned, as the final values are consistent with what is expected. But for a multi-threaded application with shared data, reordering of instructions may render inconsistent or unexpected results. Here we have an example. So as an example of that, consider these data that are shared between two threads. We have Boolean flag, which is set to false, and integer x, which is set to 0. And we are assuming that two different threads sharing these data, where thread 1 performs the statement while not flag print x, and thread 2 performs x equals 100 and set flag to true. So the expected behavior is, of course, that thread 1 outputs the value of 100 for the variable, because thread 2 is going to set the value to 100, and so we are going to print the value of x on thread 1, which the value will be 100 because they're sharing that data. So this is the expected behavior. However, as there are no data dependencies between the variables flag and x, it's possible that a processor or your compiler may reorder the instructions for thread 2 so that flag is assigned true before assignment of x equals 100. So we are assuming that we are going to set the value of x to 100 and then change the flag. But your processor or compiler can change the order of that statements. So in that case, it can change the value of flag. So if you change the value of flag before setting x to 100, that means thread 1 is going to print another value. Actually, it's going to print 0 instead of 100. So in this situation, it's possible that thread 1 would output 0 instead of 100. So less obvious is that the processor may also reorder the statements issued by thread 1 and load the variable x before loading the value of flag. If these were to occur, thread 1 would output 0 for variable x, even if the instructions issued by thread 2 were not reordered. So for that reason, we can not directly use Peterson's solution on modern architectures, because consider what happens if the assignments of the first two statements that appear in the intersection of Peterson's solutions are reordered. It's possible that both threads may be active in their critical sections at the same time, as shown in this figure. So to ensure the Peterson solution will work correctly on modern computer architecture, we must use memory barrier. In previous part of this course, we saw that a system may reorder instructions, which is a policy that can lead unreliable data states. How a computer architecture determines what memory guarantees it will provide to an application program is known as its memory model. In general, a memory model falls into two different categories: strongly ordered and weakly ordered. Strongly ordered means a memory modification on one processor is immediately visible to all other processors. Weakly ordered means where modifications to memory on one processor may not be immediately visible to other processors. So Memory models change by processor type, so kernel developers cannot make any assumptions regarding the visibility of modifications to memory on a shared memory multiprocessor. To address this issue, computer architectures provide instructions that can force any change in memory to be propagated to all other processors, thereby ensuring that memory modifications are visible to threads running on other processors. Such instructions are known as memory barriers or memory fences. When a memory barrier or memory barrier instruction is performed, the system ensures that all loads and stores are completed before any subsequent load or store operations are performed. Therefore, even if instructions were reordered, the memory barriers ensures that the store operations are completed in memory and visible to other processors before future load or store operations are performed. So let's return to our recent example in which reordering of instructions could have resulted in the wrong output and use a memory barrier to ensure that we obtain the expected output. If we add a memory barrier to operation thread 1 here, before printing the value of x, we are going to add a memory barrier here. We guarantee that the value of flag is loaded before the value of x. So actually that means do not execute that instruction before this one. So before executing the rest of instructions, we have to propagate the new value of all variables before the memory barrier. Similarly, if we place a memory barrier here between assignments performed by thread 2, so we are going to assign 100 to x and we are setting a memory barrier here, and then we are going to change the value of flag to true. So we ensure that the assignment to x occurs before the assignment of the flag. So this is how we can use memory barrier to solve that reordering problem. Also, okay, actually, we started to discuss the software solutions. Also, our modern computer systems provide some hardware solutions to critical section problem too. But before the moving hardware solutions, do you have any question? Okay, then. So let's take a break. I'll be here in 10 minutes and then we can continue with hardware solutions on the synchronization problems.